First of all, does everyone understand at least intuitively what's going on here, right? I have one disk sliding towards the other. They are not hitting head on. There is some misalignment, okay? There is some impact parameter. And when they hit each other, they stick to each other without deformation. So what happens? The combined object will have a velocity of center of mass, but it will also start rotating around the center of mass. And we would like to calculate both the velocity of the center of mass and rotation angular frequency around the center of mass. Good. So what is conserved in this problem? First of all, if these two disks are on a frictionless plane, are there any forces, net force, in that system? No. It's a closed system, which means momentum should be conserved. How about angular momentum? Well, about any point, actually. There is no torque, there is no net force, so it must be conserved too. How about energy? How many of you think energy will be conserved in this collision? Only one person? Two people? Three people? Well, those three people need to remember that this is a completely inelastic collision, which means for these objects to stick to each other, you need to form new bonds, right? So some energy will be lost. So this is not an energy conserving collision, right? So let's write, we have momentum, which is conserved. Energy is not conserved, but angular momentum is conserved. So let's start with the easiest part. What's the initial momentum? M times V, right? What's the final momentum? What was the momentum of a combined system of particles? It was velocity of the center of mass times the total mass of the system. So it's going to be 2m times v prime. So initial momentum is equal to final momentum, which means m times v magnitude is 2m times v prime magnitude. So v prime magnitude is v magnitude over 2. So part A was quite easy. Now we have to think about part B. We have already found, yes? You're right. What's the center of mass velocity of the combined two-disk system? And that's exactly what we have, okay? So, I mean, here I can see it in your eyes that you're confused, right? There are these two objects, both of them. They are both doing a translation motion. They are also doing rotation. However, we have proved that the total momentum is only related to the velocity of the center of mass times the total mass of the system. Okay? If you want, the rotational contribution to momentum is 0. Okay? Good. So first part was very easy. How many of you found this result? Excellent. Great. So now for part B, we have to be a little bit more careful. Okay? First, let's do some basics. You could have looked up, or you could have, I don't think anyone would actually calculate. Maybe you would remember that I disk around the center of mass was mr squared over 2. So how about the center of mass of, let me try to be more clean with my objects. So what's the center of mass? Where is the center of mass of this object? Exactly at the contact point, right? So what is the center of mass of this object? What do I need to do? I need to calculate. I need to use the parallel axis theorem. What did parallel axis theorem tell me you should get the center of mass, moment of inertia of one of the disks. But then you should add to that, what's the distance from that point? That's r. You should add to it mr square. And I have actually two of these objects, right? So the combined disk center of mass, moment of inertia is what? 3m r square. All right? How many of you found this? Clearly, everyone needs practice with moments of inertia and rotational problems, okay? So what I'll do is I'll actually today update the list of selected problems from the book. I'll go all the way to the end of the course. I'll also include problems about oscillations. I think it's a good idea to start solving problems before we get to the final. It looks like almost a century away from today, but it's not, right? In 3 or 4 weeks, we'll have our final exam. So, and you need practice with these angular momentum quantities. So, how about initial angular momentum? That's a good question. With respect to what? What was my advice to everyone? Always stay in the center of mass. As I'm the professor and you're the students, you should follow my advice, but I'm not bound to follow my advice. Okay? That's a joke. Come on. It's early in the morning, but even the joke is bad. It's the professor who's doing the joke. So it's kind to laugh at it. So I'll not follow my own advice. I'll actually pick up any coordinate frame. All right. And write my angular momentum with respect to basically any coordinate frame. Right. Angular momentum, we said, has two components. What were those two components? One was r cross p, but that's the center of mass momentum. And there was another component which was I center of mass times omega. So let me redraw this. In the initial case, basically just let's consider the case just before collision. Okay. This guy has V, and obviously I need to be more careful. The distance is r over 2. So initially, is my disk spinning around itself? It wasn't specified in the problem, so probably it wasn't. Okay. So what's my initial angular momentum? I have mv cross r. Excellent. R cross mv, right? That is, and m is capital M. The order in a cross product does matter. So now, what's r? R is the vector here. Right. So I basically need the following. I need r magnitude times m times v magnitude times sine theta. How about the angle here? So it's pi over 2 minus theta, right? So if I call this distance d, Sine theta is cosine pi over 2 minus theta. So it's mv r cosine pi over 2 minus theta. So it's going to be mvd. Okay? How about right after the collision? After the collision, I'm drawing it in a kind of strange shape, but I think you understand. Red is before the collision, blue is after the collision. Okay? What's my final angular momentum? Now I have two components. I've said that this is going to be v over 2. I will have r cross 2m times v over 2. And now the blue r vector, maybe let's call this r prime. Okay. R prime cross m v again. But now, the red vector was going to the center of mass of the first disk. The blue vector is going to the center of mass of the combined two disks. It's going to the contact point. So I can do the same thing. Let me call this d prime. So I will do the same thing. I'll just write this as m times v times d prime. What's this difference between d and d prime? D minus d prime is what? Because the system is symmetric, right? The contact point is r over 2 away from both centers. R over 4 away from both centers. So by geometry, I have d minus d prime as r over 4. But is that the only source of angular momentum in the final state? So this is not. This is just the center of mass contribution to the angular momentum. I also have this object rotating around itself, right? So I must actually add to it L final is mv d prime plus I center of mass times omega. Right. Now I can say initial angular momentum is equal to final angular momentum. Initial angular momentum was mvd. Final angular momentum is mvd prime plus I center of mass we have calculated as 3 mr square times omega. M's I can cancel now. V times d minus d prime is 3 r square. Omega d minus d prime by geometry is r over 4. So 1 power of r cancels. Apparently, omega is 3/4. That's excellent. Thank you. It should be v over 12r. How many of you actually found this result? 3 people. That's okay. That's encouraging. It's better than 0. But I think the point of the quiz here is, first of all, you are. I mean, the concept of angular momentum is new to you. You need to solve as many examples as you can so that you develop a understanding. You develop some gut feeling about angular momentum. Okay? Yes. Louder, please.
Why we don't use angular
We could do that. You should do that. Your professor told you that. I just wanted to show you that you can do it more generally.
This took more time than I thought.
Of course it did. Yes, but it took more time, but the time is not the issue. The issue is to see that the definition, once I change my definition of angular momentum to include both the center of mass component and rotation around center of mass, now I can actually do conserve angular momentum in any frame I want. Okay? Good. So that's all I want to say about angular momentum. But please solve as many examples as you can. I can see that most of you do not have a good understanding of this subject. You need to prepare for the finals. All right? Let's talk about a nice, somewhat conceptually easier subject. Let's talk about oscillations. So, I'll start with the simplest system. Okay, I'll just take a mass m on a frictionless table, tie it to a spring which is tied to a fixed point. The spring has spring constant k. And I'm wondering the following. If I stretch this spring by some distance a, and I let go from this configuration, what is the position of the particle, position of my mass, as a function of time? Well, intuitively, I know what's going to happen, right? I mean, all of us have tied something to some mass to a spring, even if we don't realize it. It's going to do oscillations. It's going to go back and forth. But now let's try to put some mathematics into this. Right. So what I'll do is, let me choose my coordinate axis. Let's say that's my x, and x is equal to 0 exactly at the equilibrium point, exactly at the relaxed length of the spring. So now at any moment, if my spring is stretched by x, what is the force acting on it? The force law for a spring was minus k times x. Why do I have the minus sign? Because if I actually increase x, the force is trying to pull it back to the equilibrium point. And this relation actually works when x is negative too. When x is negative, when the spring is actually compressed, well, the spring, not the mass. The spring is compressed. If x of t is negative, then my force is in the opposite direction. It's positive. So my relation is correct. F is minus kx, right? Now I can drop the, because I am in 1D, I can basically write this as scalar. I'm in one dimension. So how do I find x as a function of time? Well, I need to use Newton's equation, right? I know that f is equal to ma, or I know what f is, minus k x of t is ma of t. And remember what acceleration actually was. Acceleration is the second derivative of t. So I can write this equation as d square x dt square a is minus k over m x of t. Now, this would be an ideal place to scare all of you. I could say, this is a second order homogeneous differential equation, and differential equations you're going to study only in the second year. Right? That would be a way to scare you. So you have no hope of understanding oscillations without that. But that would be a lie. I would be a terrible instructor if I do that. It's really irrelevant what we call this equation. Obviously, this is not the kind of equations you know how to solve from high school. It's not an algebraic equation. This is not 5x is equal to 10, right? Here, x is a function of time, and it's apparently related to the derivatives of x. So any equations which contain a function and its derivatives, they are called differential equations. That's the name. But you learned some calculus. You know how to take derivatives. So what's this equation essentially telling me? It's telling me that x of t should be such a function that the effect of taking two derivatives is just a minus sign times a constant in front. Do you know any function which is equal to minus itself when I take two derivatives? Sine and cosine, right? If I actually have sine, I take a derivative, I get cosine. I take another derivative, I get minus sine. So apparently, sine, let's say u, if I take two derivatives, is minus sine u. Similarly, if I take two derivatives of cosine u, I get minus cosine u. So that's excellent. That's great. So I know that my equation is at least satisfied by some kind of function which will be a sine or a cosine, okay, or maybe a combination of both. Now the important thing, why do you actually need a course in differential equations? What you're going to learn in differential equations is that once you actually find two functions which satisfy a equation that has second derivatives, your solution is unique. You don't need to go looking for a third function. Okay? You don't need a third function. Two functions satisfying a differential equation is enough. I am being purposefully vague. I'm not being mathematically consistent. I'm just telling you, if you see this equation, the solution is either a sine or a cosine. To generalize that, you need to learn a little bit of more mathematics, which you'll do, most of you will learn next year. Okay? But now, I'm actually quite happy. What I'll do is, I'll guess the solution. I'll say x of t is a constant times sine another constant. I'll call it omega. And why do I actually need that constant? Because when I take two derivatives, I not only want the minus sign, but I also want a constant multiplying my function, right? C2 of cosine omega t. All right, let's take a derivative dx dt, the first is when I take the derivative of sine omega t, I get an omega outside. It turns into cosine. When I take the derivative of cosine omega t, I get minus omega c2 cosine omega t sine omega t. Let's take another derivative. D square x dt square. When I take a derivative, I get a minus omega out, so minus omega square c1 sine omega t. I get plus omega out, so it's going to be minus omega square c2 cosine omega. Let's see, does this satisfy our differential equation? What was our differential equation? D square x dt square was minus k over m x. So left hand side, let me write as follows: minus omega square c1 sine omega t plus c2 cosine omega t. And right hand side is minus k over m. And x, I know what x is. X is c1 sine omega t plus c2 cosine omega. Hey, that's great. My guess does satisfy the equation if omega square is k over m. An equation is satisfied. Well, that's great. I already found one of the constants in my solution. But that's not very satisfying, is it? Because I know I said my solution is c1 sine omega t times c cosine omega t. How about c1 and c2? Where do I find c1 and c2 from? And that actually, I did not use one important thing in my solution. So far, I did not tell my equations where I started from, which sort of initial state I started from, right? So I need to determine C1 and C2. We need initial conditions. What was my position at x t equals to 0? What was my position at t equals to 0? I said I start from point A with 0 velocity. So here is the thing. X at time t equals to is 0. Dx dt at time t equals to 0 is 0. So what was x? X time t equals to 0 is c1 sine square root of k over m times 0 plus c2 cosine square root of k over m times 0 is a. What's sine 0? 0. Cosine 0? 1. So here I find c2 is a. How about the derivative? When I take a derivative, c1 omega times cosine square root of k over m times 0 minus k over m c2 sine square root of k over m times 0 is 0. Sine 0 is 0. So this is cosine 0 is 1. From here, I find C1 is equal to 0. Oh, that's great. Now I've actually set out what I wanted to do. I found x of t is a cosine square root of k over m times t. What does that look like as a function of time? At x is equal to, at t equals to 0, I'm at a. And we all know what a cosine function does. It oscillates, right? What is the minimum point? How far away do you get from the original? It goes to minus a because cosine goes from 1 to minus time. At which time does it go to minus a? Well, cosine must be minus 1. So inside of cosine must be pi. So it's going to be, let's call t0, must be pi over omega. Or when does the motion repeat itself? The period of the motion will be 2 pi over omega. So let me just tell you a few nomenclature of oscillations. The change, well, how much you oscillate, or A, is called the amplitude. Omega is called angular frequency. T, which is 2 pi over omega, is called the period. Sometimes people also define nu, which is 1 over t, which is omega over 2 pi. That's also called frequency. Okay. Now we'll see that this kind of cosine or sine, which I'll call sinusoidal behavior, is common in all oscillations. The moral of the story, the thing we're going to do in oscillations, is to try to get back to a differential equation like that in every system we actually try to solve. Yes? Derivation regarding what? When we were finding constants. C1 and C2.
Yeah, so there was a letter A, variable A.
Yes, that was given in the problem. That was my initial, how much I actually stretched A. How much? Okay. Now, as I told you today, there are 2 quizzes. We've already done the first quiz.